So optimization is the name of the game in 4.5. What these are going to be is word problems that involve absolute maxes and mins. So the good news is, foundationally, you're strong at doing absolute max and min problems. That was from 4.1. We did local mins and maxes, we did absolute mins and maxes, and we were pretty good at the absolute min and maxes. Here's a shortcut that we can use to decide max and mins now that we had a lesson from 4.2 where we did the second derivative, which actually can help us back in history a little bit. If the second derivative was negative, what was that called from 4.2, the day that we used first and second derivatives to graph things? A C word that we don't usually say or write. But there's another word we were usually writing. We were doing like increase, decrease from the first derivative. And what did the second derivative do for us on graphing?
Concave down.
Concave down is the word we were looking for. The second derivative, if it's negative, tells you the shape is concave down. What does that mean? It's like this. A shape like that, does it have a maximum point? Or does a shape like that have a minimum point? Keeping in mind that would go for literally forever.
A max.
That would have a max. So if you ever have like a thing that you're not sure what it is, if the second derivative is available to you, doing the second derivative, if it's negative, could reveal for you you have a max. What if the second derivative is positive? That would be concave up, and therefore that would have a min. That's not a superstar section idea of this section, but it's a nice tool now that we can add to our toolbox. If you're trying to decide if you have a max or a min, that's another way we can do it, in addition to what we were doing with our normal process back from 4.1. Here's my general strategy is for these word problems. Step one, maybe make a picture. Sometimes that's helpful. Sometimes it's not. Sometimes it's done for you. Sometimes it isn't. But picture is a maybe. For sure, you're going to have to write your equation, and that's where I throw an exclamation point down on that, because that may be hard. It may be hard to write an equation for a story. That's why people get paid a lot of money to do engineering projects, things. Like, it's not always easy to take the story and figure out what the math even is. It's usually easier to do the math once you have it than it is to like create the math. And that sometimes is going to be the hang-up on this. And then we're just going to run through the absolute min-max process like we did from 4.1, which I'll remind you of once we dig in and do it. But that's like the nutshell of an idea, where the idea of this isn't hard, but the devil, as they say, is in the details sometimes. Like carrying out all these problems, some of these are going to be tricky, like the word problems on pretty much every subject always are. So I'm going to just work through the 4 book examples. So if you want to join me on 234, 234 says, example 1, metal fabrication. An open top box is to be made by cutting small congruent squares from the corners of a 12 by 12 inch sheet of tin and bending up the sides. How large should the squares be cut from the corners to make the box hold as much as possible? And you read that and think, what are you talking about? At first, probably, right? So I have my visual aid that I put in my folder every year. So here's what they have in mind. They have a sheet of metal like this, and they clip out these corners, and then they're going to go foldsy, 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 and make like a little box out of it. That's what they have in mind. Like the kind of box if you buy a case of pop at Sam's Club, you buy 24 Fagos, you get one of those boxes. Sometimes water bottles, they've got a box like that at the bottom that's helping us contain things. But they're trying to make a box like that by cutting out corners and folding out the shape. And they want that box to hold as much as it can hold. So I would say picture here is helpful. So we had the original sheet of metal was how big?
12 by 12.
12 by 12. And then we cut out some corners. Do we know the corners, what those are? No. So X and X on all those little square corners. And then we're imagining that we'd fold that up and make like a 3D box along my like fold lines. And we're trying to figure out what's the most that box can hold. So what's the math word for how much space there is in a box?
Max. Volume.
Volume. How do we do volumes of a box? Length times width times height could be a starter point, but I don't know if I'd even write that down, but don't get married to it because that's not going to stand the test of time. But that's a picture and that's an equation and we're getting started and that's decent. Question them all, stuff so far. Okay, what is the beginning of the absolute min-max process? How do we do absolute min-max? Do the derivative. You would not want to do the derivative of this because you have three things. It would be like a double product rule. So you don't want that. What we'd like to do is get an equation, preferably with one variable in it, if that's possible to us. Like on cone day, we jumped through some hoops with cross-multiplying on cone day to just get one variable instead of two. Some of that may be necessary on this, and it likely is. So let's look back to our picture. How long is this box now that we like cut out stuff and like folded it? What's this dimension of box? How wide would the boxy part of the box be? 12 minus 2x. How much would the box be this way? Also 12 minus 2x. How much would the box be coming out the board at you?
Would be 2 times that.
When you hear it, you'll go, oh.
Another 12 minus 2.
Nope. So like here's my box. I've cut X, 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 X. Every cut piece is an X. That box is pretty wide. That box is pretty tall. Those are 12 minus 2 X's. Imagine it's a square in my paper, which it isn't. But how far is the box coming toward you? Not very far, but how much is
2x?
No. How far is this?
X.
It's just coming out an X. Does that make sense so far? Okay. Would you want to do the product rule on that? You want to do the derivative right now? Not so much. What would you be better to do? Yeah, just multiply this all out. So a pair of 12s would get you 144, but with that X in the mix as well. This foil combined with this, with the bonus X squared, so negative 48 X squared. These foil with the bonus X. That's the part that makes these problems hard. It's just the hoops you have to jump through at the beginning. Question come up there. Now we're good. Now we just do our process. The process is do the derivative. The derivative may be easy or hard to do. This is an easy derivative to do. Derivative of this would be 144 minus 96x plus 12x squared. That stuff, when we foiled it, it ended up kind of out of order for how you might usually like it to be in descending order, so we can rearrange that if you want to. We're always, for our process, trying to think about if the derivative would equal 0. We could solve this one of two ways. To solve this equation equaling 0, what's a thing you can do? You could factor. What else could you do if you're just not in a factoring mood? Punch in your quadratic program, because it's a quadratic equation. So factoring out of 12, it'll factor just fine. If you wanted to go down a factoring path, it's going to be a pair of minuses, 6 and 2 would do the trick. If you want to run your quadratic, we'd get 6, we'd get 2. That's the two possibles for the x's. Those are our critical points, to use a word from 4.1. So if we have an x of 6, we need to figure out what the volume would do. If we have an x of 2, we need to figure out what the volume would do. Where would we go to figure out what the volume is going to do? Right back here, I'd probably go there, is where I'd most like to put my x's in, but you could go here. Anywhere before you did the derivative would be fine. If we put in a 6, what would we get out of that when we put in a 6? 0. If we put in a 2, we get 8, 8, 2. 8 times 8 times 2 is 128. So this pairing is the min, because 0 is low. This pairing is the max, because 128 is higher than 0. And then it's a question of what did they ask you? And then sometimes that's what gets hard, is at the end to interpret, like, look, what do they even want now for me to do this? They might ask you, what is the maximum volume itself? And maybe you want the 128. They could ask you what the corners were cut. That would be the 2. They might ask you for the 8 by 8 by 2 dimensions of the box that we just had a second ago. Maybe they want the dimensions of what the box is going to be. Maybe they want something else. Maybe they want to know how much of an area of cardboard was left on the floor when they cut it. And then you've got to go like 2 times 2 is 4. There's 4 4s. There's 16 square inches of stuff on the floor. They can ask almost anything. And that sometimes is a pain. On this, they ask you how large should we cut those square corners to do a big box. So big box, cut the corners to be 2. That's what we see. But they could ask a lot of stuff at the end once you've done the math. Question about that one. The other thing that makes this challenging is every question's kind of different. Like, you're not going to now do the homework and have like, okay, I understand this box thing, I could do that, and then you do like 6 of them for homework. And you're like, yay, I got the boxes figured out. There's probably like 1 box in the homework. And so you master the box, and then you can do the pump roll. That's another challenge for these. Anything there before I move up one? So example 2 says you're designing a 1 liter oil can shaped like a right circular cylinder. What dimensions are going to use the least amount of material? So liters is a measurement for volume. So they're telling you that the volume is a liter. I can see just from peeking something that I was curious if they would do. There's some occasional metric unfriendliness in this, like there are in everything. Like liters are not always consistent with other units. Sometimes milliliters are better, because milliliters can be friendly with centimeters. It's just a better friendship. So they did make an adjustment here on this. Instead of using the 1 liter volume, they're using 1,000 milliliters for the volume. They're talking about a cylinder. So volume of a cylinder is pi r squared h. That might be something that we want to look up or know or write down or have in the notes or something. Volume of a cylinder is pi r squared h. And that's equal to 1,000. Here's another thing that's true of most of the questions that wasn't true on this one. On a lot of these questions, there's going to be 2 equations. There's going to be one equation that just provides you some relationships, like the cone did, where we would do the ratio triangles and use that to just cross multiply and make substitutions. That's what this is. This isn't something for us to do the derivative of. We're not trying to figure out the most volume or the least volume. The volume is set. The volume is 1,000. We're not wiggling on that. What we're trying to do the most or least of is the material used. But that's not the volume. If I want to talk about what fits in that box, that's the volume. If I want to talk about how much cardboard it took to make that box, what is that? Another word for shapes. Every shape has a volume, the space in it. Every shape also has something else that's like the surface area. So we're going to need to make a surface area equation and do the derivative of that. So maybe a note you want to write of something I'm saying is you always do the derivative of the thing you're trying to maximize or minimize. So if they say what's the most volume, what's the most surface area, what's the least area, the least radius, the least whatever they have that's a most or a least, that's the equation you want to do the derivative of. But there's frequently another equation afoot that's going to help you make some substitutions. I doubt if you know how to do the volume of a surface or surface area of a cylinder. I don't think we've ever done that together in your life. I think that we're breaking new ground today. Surface area is just like the space of the surface. So I guess one place you could start for surface area would be that this, for a cylinder, has a surface area. You can do the area of that piece. What would the area of this piece be? Close.
Or
Area of a circle? Pi squared. How about the bottom? Pi squared. We have 2 of those pi r squareds. Plus, what else do we have? Where else is there some surface area? Yeah, like the round part. So we would also need to measure this, which is, you said it earlier, I shot it down. 2 pi r does the circumference. But that circle, that circumference, also has a height. So the total surface area of a cylinder would be pi r squared for the top circle, pi r squared from the bottom circle, 2 pi r for the circumference of it, but multiplied by the height of that thing. And I don't think you could have done that by yourself. You might have had to Google that. And I don't think you have to create any formulas in the homework that are quite that intricate. So if you're thinking, oh no, am I going to have to create all these million formulas like that? I don't think so. But like I said at the beginning though, sometimes writing the equation is a challenge. You don't want to do the derivative of this yet. You do want to do the derivative of this. We're trying to do the least amount of surface area is our goal. We will want to do the derivative of this, but not yet, because it doesn't just have one variable. We want to have one variable before we try to take on a derivative. And that's why this existed. This existed so we could do some sort of a substitution. Would it be easier to solve this for an R, or would it be easier to solve this for an H? H for sure, because if you solve for R, you have to do square root. There is at least one homework question where you get stuck with a root. I guarantee that. I'm positive of that. This is not one of those. Here we could get the H alone. It would be 1,000 on top of pi r squared. We can stick that in here and have a better equation for derivative purposes, which would be 2 pi r squared plus 2,000 from 2 times 1,000. What would happen to the pi's? They'd cancel. The r would cancel some of the r squared, and we'd get an r on the bottom. I'm going to write that as r to the negative 1. Question about that? Breathe a sigh of relief, because now we're on a familiar path again. Now it's time for us to do that absolute min-max thing, which always starts off by doing the derivative, which is 4 pi r.
Are we not doing like DRs?
No.
Okay. Negative 2,000 plus -2.
Yep. And we're always worried about the derivative trying to equal 0. Maybe you want to rewrite this to make it a little more algebra familiar. Instead of r to the negative 2, bring back like the fraction style. That might be a better looking thing. A suggestion on how to solve that.
Add 2,000 over r squared.
Yeah, let's get them on 2 different sides. So 4 pi r would equal 2,000 over r squared.
And multiply both sides by r squared.
We could, so 4 pi r cubed is 2,000. And you might as well divide the pi. So 2,000 divided by 4 pi. To get the r completely alone, cube root that. And you're going to have to just go calculator and round. Generally speaking, I'm not a fan of go calculator and round, but like on this circumstance, we just need to go calculator and round. And this is going to come up with a radius of around 5.42. Here's a problem. If we plug that number in to get a surface area answer, we can take this 5.42 and plug it in, and we can figure out what the surface area roughly is. Why would you have no idea if that's a max or a min? You only have one. You don't have anything to compare it to. Okay? So we have 2 choices. If you only have one number, which gives you nothing to compare it to, you can do one of 2 things. One thing would be pick any other radius that would seem practical, something you wouldn't mind plugging in, like 1. I could pick a radius of 1, and I'm not going to do it this way. But I could pick a radius of 1. I could figure out what the surface area is. I could plug in the 5.42. I could figure out what the surface area is. If this is bigger than this, then we found the max. If this is smaller than this, then we found the min. We could do that. There's nothing wrong with that. Sometimes I'll do that, sometimes I won't. This time I won't. But we could just pick another number so we have something to compare it to. What I would do is actually the second derivative. If I do the second derivative from here, I get a 4 pi plus some other thing that I don't even care about, because the only thing I care about is whether that second derivative is positive or negative. On the thing we talked about at the beginning when I came in, the concave up, concave down stuff. So if I do the second derivative, it would be 4 pi plus some stuff. That's definitely positive. So that's definitely concave up. So this is definitely something to do with the minimum. We wanted to find the minimum, use the least amount of stuff to make our container. So we're on the track for the answer. They never asked us to find the surface area, so we don't care. They did ask us to find the height. Where can we go to find the height? The top. To what part of the top is best to find the height? The h equals part. H equals, just plug into that the 5.42 that we found, and I'm going to take a peek, see at their answer to say it's about 10.84. Good lesson from that one. For sure, there will be some in the homework that you're only going to get the one critical point, and then you have no way to know if it's the max or the min. And then you've got your choice of either create another number to have a comparison contest or to do the second derivative. Sometimes like this, the second derivative wasn't bad at all to think about. To just decide if it's positive or negative, that's not bad. But sometimes the first derivative is such a shambles, you would not want to do it again. And so sometimes it is more effective to like pick another number. Something about that.
How did you know it's going to be positive?
If it's 4 pi plus up, like this is going to be, radius is guaranteed a positive item.
Yeah.
So you can't have a negative radius. So if it's going to be 4 pi plus some radius stuff, it's got to be positive. Something there. Let's go again. This one's not bad. So example 3 said, this is just like almost a straight out algebra 1 style like story problem. It says find two positive numbers whose sum is 20. So like x plus y equals 20. It's just a thing. That's not what we're going to try to do the derivative of, because they didn't use any kind of word about most or least yet. So it is not derivative time. This is like a simpler version of this. This is just there to help us make some substitutions. So sum of two numbers is 20. Then they say we want the product as large as possible. So the product would equal x times y. That's what I want to do the derivative of, because it said find the product as big as possible. So I need to do the derivative of this. Question about that? Why don't I want to do the derivative of this yet? More than one variable. So I need to either go x equals or y equals, doesn't matter, your choice. Y equals, y would equal 20 minus x. So this could be x times 20 minus x. In other words, 20x minus x squared. And then we can kind of go, we're done with the hard part now. And that hard part was an easier part than average. Now the process is do the derivative, which is 20 minus 2x. We always like that derivative to equal 0. If we solve that for x, x would be 10. If x is 10, then y is 10, which means the product is 100. And that's either the max or the min. We have no idea which one. We found something, but we have no idea what we found, because that's one of a kind. Question about that? Okay, so to figure out what you found, you could do one of two things. You could either pick another x that's practical to work with. X's plus y's are supposed to add to 20, so pick any number that making it add to 20 isn't going to be a big fuss. 5. 5's partner is 15, where the product would be 75. So this was a max. And our goal was to find as large as possible. So we did it. So the answer is something in here. The question is to find the two numbers. So a pair of tens, that's the answer that they sought. If they wanted us to tell them what the product was, maybe 100 could have been the answer. Or maybe they want to be ridiculous and say, what's the difference between the two numbers? And then it's 0, or something crazy like that. The fun part, and I think it'll happen in one of the homeworks, and it's a conversation for another time. What if we had found the max, and the question actually wanted the min? And we ran out of numbers. Like, we only had one number. It was the max, and they wanted the min. How do we salvage that problem? And there is a way. Sometimes we can actually do that, which seems impossible, but it isn't. But that's not a this moment question. That's another time. So if you do any where you find the max and they wanted the min, we'd have to talk about that. Example 4, geometry, says we're going to inscribe a rectangle inside a semicircle of radius 2. What is the largest area that rectangle can have, and what are the dimensions? A picture is going to be necessary, I think. The area is what we're going to want to do the derivative of. There's probably some other kind of equation that's afoot. Maybe not, I don't know. But we want to do the derivative of the area, because it said, what's the largest the area can be? So we need an area equation for a rectangle. How do you do areas of rectangles? Length times width. But chances are that's going to take on a foiling look in a minute. You know, knowing that area equals length times width, that's like back there when we knew volume equal length times width times height. That wasn't a permanent solution. That was just a temporary filler to help us feel a little bit better. But there's going to be some rectangle here. We're going to want to go length times width, but that's probably going to be some foiling. That's what we'll want to do the derivative of. If you turn the page, there's a picture that can help us. There's a bit of circle knowledge from way back in chapter 1. Anytime they do circles, the equation of a circle is x squared plus y squared equals radius squared. So we've got a circle like this. They did a semicircle. They said the radius is 2's. So the equation we're working from is x squared plus y squared equals 4. That's what the equation is of this. Some of these inscribed ones, they'll draw the picture for you, and that helps you. To be inscribed means you like jam it in there, a rectangle, where it's going to have its vertices touch on the semicircle. So that's an inscribed rectangle. For now, I could call that x, which means this would be another x. And for now, I could just call this y. Because I don't really know what that is either, but that's something that's not too radically confusing. I'm going to create myself a little more space. I'm not going to need another equation there, but the area is the length times the width. What's a better name now for the length? Just of the rectangle, not of this, just
2x.
2x is the new length. What's the height of the rectangle? Y. Why is that not something I'd be super excited to do the derivative of? There's 2 variables. But we have this. This gave us an XY relationship through the world of circles. It doesn't really matter if you get this x equals or y equals. So pick one. Y equals. What would y equal? Yeah, we'd have to subtract the x squared, and then we'd have to do a root. So this new area formula is 2x root 4 minus x squared. You're a little bit happier because you have one variable, but you're a little bit grouchy because you have a product rule to do, and there's a root on one of those pieces. So So we've got, at best, mixed feelings about this. Maybe you want to write this 2x and then stuff to the half. Maybe that's better. But we're going to have to do the derivative. Okay. Usually this is the part where we go, okay, the hard part's done. It's time for me to just do my process. My process is to do the derivative. Generally speaking, all the derivatives on those first three were pretty easy. But I had forewarned you, sometimes the derivatives aren't that much fun either. There aren't a lot of bad derivative moments, but this is one. Like I said, the overview of this isn't bad. The devil is in the details. There's just a lot of steps where something could be harder than you want it to be. You wish they were all like this. That felt nice. That was nice and clean. This one isn't as clean. Derivative time, so I have to go, I look at this as my first, I look at this as my second, and for my derivative, I go ahead, I'm going to go where I have a little more width to work with here. We're done with this. I'll just backtrack a smidge to give myself a little more width this way. So I'd have to copy the first times. Derivative of the second is going to be a chain rule. Abby did not enjoy that news, anybody who watches this video later. On this chain rule, we go half copy to the negative half, and then the derivative of the inside piece is a negative 2x. The plus for the product rule, we still have to copy the second one, and the derivative of the first is a 2. So let me make sure I have that all good, which I think I did. Copy the first, derivative of the second is half stuff, the negative half, times derivative of inside, plus copy second with the half still there, derivative of first is 2, and I agree with all of that. Yeah. Clean up 2 times a half is a cancel. We like the derivative to ultimately equal 0. There's a negative 2, there's an x squared. And instead of stuff to a negative half, I'm going to return it in fraction form, negative power to the bottom, half as a root. This, I'm going to just leave it 2 and bring back the root. And I'll pause there. Do you need me to rewind anything? Did I lose you anywhere? Are we still hanging in there? How would we solve this?
Split. Like a one on this.
Yeah, move one of them. Okay, so let me move this one, and it would just become positive 2x. And that would slide the equals, so the equals is between them. And this is going to get better fast now. It looked awful. It'll get better fast. I cancel the 2's just to make my life a little bit simpler. The mutual 2's are cancelable. Then what would you want to do?
Multiply root 4 minus x.
Multiply the root times the other root. And when you multiply roots times roots, the roots just disappear. So there's an x squared equaling a 4 minus x squared. And all of a sudden we're like, oh, okay. Now we're talking again. This is a little bit better. So 2x squared is 4. So x squared is 2. So the x would be root 2. Probably we'll need to go get a y. Where's the best place to get a y? Hopefully there's something that'll be y equals. And do we have a y equals? Yeah, let's go use that. So, and we don't need to even put the root 2 back in and square it. We knew x squared was 2. So maybe you just replace the x squared with the 2. 4 minus 2 is 2, root it. The y would be root 2. If we go to look at what the area actually was, the area involved multiplying an x and a y and a bonus 2. So this times this with a bonus 2, that's an area of 4. That's something. Is it the max or is it the min? We don't have a clue. We have no idea. But we're almost there. You have two choices. One choice would be to do the second derivative. Would you want to do another derivative like that? No way. No way. So we're not even going to touch that. We're not even going to think about that. Just pick any other number that's user friendly. I'd say 1. If x is 1, what would y be? Root 3. And if we take 1 times root 3 times 2 root 3, what's bigger between 4 and 2 root 3? 4. So this stuff would be the max stuff, and they wanted us to do what's the largest area we can do and what are the dimensions. So the largest area we can do is 4. One of the dimensions is the root 2. The other dimension was 2 of those. Because remember, the original width of this was 2 of the x. So the one, that would be the other dimension. The syllabus will give you what to do. We'll be doing this obviously for a couple days. I'm not planning to try to do anything new until the Tuesday before we go on break. So I'm thinking tomorrow we look at homework. I'm thinking Monday we look at homework some more. Probably after 2 days we'll look at the homework. We're settled-ish, and then we venture on to 4-7 probably right before break.